so sorry. Oh. Oh. Wowza. Well, you know, allergies can develop at any time in life. And they can disappear at any time in life, too, which is crazy. Okay, here we go. We are doing more transformations. We're going to spend, like, kind of quite a few days on transformations because it is really important that when we look at a function, we have a general idea of what it looks like, its overall shape. That's the parent function. And then how do the numbers affect that graph? And so last week, we did rigid transformations. That's what we talked about. And rigid transformations, they take the basic shape, and all they're going to do is move it up, down, left or right, or maybe reflect it across either axis. So rigid transformations are all these here up top. So we're going to review real fast. So here I have, in this case, this is a parent function. What function is this? X squared. Very good. And so this is, well, we're gonna call it a generic name. We're gonna call it f of x. All right. It's just a generic function, f of x, and I can take my f of x picture, just the picture of it, and if I subtract a number, what would that do? If I take my function and subtract 4, what would it do? It would move down 4, yeah. And so I'm going to subtract, I'm going to use k, that's how we normally see it. And so if we have some number on the outside, like a 4, and its subtraction, that's going to shift our graph down 4 units, or in this case, it's going to be down k units. So it just takes it and slides it down. And what should I write to shift it up? F of x plus k. Very good. So the plus k is going to shift it up k units. So that k is outside the function itself. And anytime that thing is outside, a number is outside, it's going to affect y values. Okay? Now, when it's inside with x, that's going to shift our function left or right. So I'm going to write f of, if I write x plus a number, what way would it shift it if I wrote x plus a number? Left, it would go left. So I'm going to do h. H is for horizontally. So it moves it, in this case, it's going to move it left, and so it would slide it to the left h units. And if we want to move it right, then my number would be inside. And what should I write? X minus the h. Yeah, everything with x is always sort of inverted. It's never normal, okay? It's never quite what it seems. All right. Now, if I have a reflection in the x-axis, or I don't like the word in. I usually change that to across. A reflection across the x-axis, or you could say a reflection over the x-axis. So what's happening here is, like, imagine this is the point, I'm going to say it's like the point 5, 2. Let's pretend, all right? So that's the point 5, 2. If I reflect it over the x-axis, then what happens to the point here? So what does it become? What's its new 5, negative 2. So that affects the y value. So what we do here is we have our function. The x doesn't change, but the function itself goes from positive to negative. So that's what we're saying. When that negative is on the outside of the function, it's changing the y coordinates, okay? Now, a reflection across the y-axis, let's look at an ordered pair again here. Yeah, so we have, again, let's pretend this is the point 5, 2. And if I reflect it across the y-axis, what's its new ordered pair? Negative 5, 2. Yeah, so in this case, the x is turning to the opposite. So in function notation, that would be the opposite of x, all right? And the y value stays the same, which is kind of interesting. This is all function notation, kind of crazy. But what we're really talking about today are non-rigid transformations. Non-rigid transformations distort the shape of the function by changing the size. So we can dilate functions. That means the same thing. Your pupil dilates, it changes size, okay? And so that's what's happening with dilations. Here we have vertical dilations. A vertical dilation is changing the y values, all right? And we can stretch or compress the y values based on putting numbers in certain spots, okay? So here I'm looking at my regular function, and I like to do this with a calculator, so. All right. So let's say I'm looking at a basic parent function like x squared, and what I want to do is I'm going to put a number in front of this x squared graph, in front of my parabola. So I'm going to do 4x squared, okay? And what I want you to see, we're going to look at the table. You can see in blue is the table. And we're going to compare the y values, because I think this is just really great. So my original parent curve goes through 1, 1, 2, 4, and 3, 9. Let's focus on 2, 4. What happened to the y value? It quadrupled. It multiplied by 4. And so what it's doing is it's taking like a normal point, like maybe the point 1, 1. And if there's a number out in front, it's changing the y-coordinate, and it's multiplying that y-coordinate by whatever that number out in front is. And so in our case, if it was 4x squared, what happened? What does my y-coordinate become? So 1, 1 is going to turn into, so does it change the x-coordinate? Yeah, the x stays the same, but we multiply just the y value by 4. So what happens is it grows a whole lot, and it becomes 1, 4. And so that's why it's called a vertical stretch, because all it's doing is taking our original point and multiplying the y value straight up by 4. So it's really stretching out. When I teach this normally in like Algebra 2, I call it the Buddha baby phase. When you have little babies, when they're about 9 months old, they're like super chunky. And they have little wrist cuffs and little knee cuffs and like jelly rolls in the belly and jelly rolls in their thighs. Like, so they're little Buddha bellies, little Buddha babies. But then when they turn 1, they start walking and they just stretch way out. They still weigh the same. They're just taller now. All right, and that's what's happening with our function. When we have a number in front, it's multiplying the y-coordinate and making it grow taller. So that is a vertical stretch. If I have a number in front of my function, that number in front multiplies the y-coordinate, a times the y-coordinate. I like to write that down. And that's what f of x is. F of x is just the y-coordinate. It's the function value. So it's just a times the y-coordinate. All right. So then, if I have another number in front that is less than 1, all right, if a is like, I don't know, I'm just going to use a again, but let's say a is less than 1, like 1/2 x squared. So now I have a number in front. Here's my regular graph. What's it going to do to the y-coordinate? It's going to shrink it, yeah. Because again, it's going to take the y-coordinate and it's just going to multiply it by 1/2. Well, 1/2 times 1 is 1/2. And so that point gets shrunk lower, all right? And so the x-coordinate stays the same, but now we just multiply our original y-coordinate by the 1/2. So again, a times f of x, really it's just whatever a is times our y-coordinate. And if you really understand what's happening here, it becomes really easy. So we call it's a compression when we're multiplying by a number less than 1, because it's getting shrunk. All right, and if it's a number greater than 1, we call it a stretch. A function will compress or stretch vertically by a factor of a. All right, so today we're really focusing here on horizontal dilations. So this would be horizontally in the x direction. And so I'm going to use, well, I can use the same parent graph here. Again, horizontally is the x-axis. And everything with x is always totally messed up. And so if I have, again, I'm looking at a regular point here, like on my regular x squared graph, I have the point 1, 1. And horizontally, let's see what happens when I put a 2 inside. And you see how that 2 is inside the power? It's really interesting there. So it's inside with x, okay? What do you think that's going to do?
Well, 2x times 2x.
Well, this is true, which is kind of interesting.
Make it 4x squared.
4x squared, this is true. What do you think at the ordered pair level? What do you think is going to happen to the ordered pair here? The x will change. Is the x coordinate going to multiply by 2, or is it going to divide by 2? It's going to divide by 2. Let's see what happens here. So if I look at the table again, my normal point here is 1, 1. So I'm just going to write this down, 2x quantity squared. So here's my example. I'm going to look at the table, and here's my normal point, 1, 1. Whoa, what happened? Oh, you can't see. Oh. Darn, I chose the wrong. Well, I'm not going to use it then. What happens is, there's our normal graph, and what happened is, this point, which was at 1, 1, now has slid. Sorry, I lost the track. There we go. Oh, I want to be on the blue curve. X equals 1/2. Oh, what did I do? 0.5. Sorry. 0.5. 0.5. The y value stays the same, but the x actually divides by 2. So that 2 divides the x-coordinate, which is really kind of interesting. So it shrinks it horizontally closer to the y-axis. So that x value became 0.5 or 1/2, 1. The y-coordinate stays the same, and the x-coordinate gets divided by 2. It does the opposite. It's very weird. So a compression happens if we have our function, and we've got a number inside with x. It actually divides the x-coordinate by b. All right, it does the opposite. It's inverted. Everything with x is totally weird. What if you have a number like f of, let's say it's 1/2 x quantity squared. What do you think that's going to do? The number in front's a fraction. It flips it. So instead of, this is going to actually, so if you have like 1 over a number, we have to flip it. It's not really, it's dividing by 1 over b, which turns out to be b times the x-coordinate, which is really weird. I shouldn't have started with this, you guys, because I actually have a worksheet where it's easier. So this is what we really want to do. Let's actually do problems. I hate general things. Never a good place to start. Sometimes, like if I taught pre-cal again, I wouldn't do it this way. I would start with this thing. And then we'd go to the rules. All right. Yeah. Let's start with actual math first. So let's see how this really works. and I am too close here. Let me zoom out a little. There we go. That's a little better. Okay. So starting with, I want you to show point transformations because that's really important for this. Label each graph with the function identifier. So you'll notice this is F, G, H, and J that have different names, so we can keep them separated. So I'm going to start with number 1 here. I'm going to graph the square root of x. What does the square root of x look like? Swoop. Hey, I love that you're learning my language. It is the square root swoop. And if you know this is square root swoop, then you know that it goes through 0, 0, 1, 1, and do you know this third point? 4, 2. Very good. So this is our parent function, f of x. And I'm just going to call it f, okay? Now, I want to graph 3 times my function. What is going to happen when I have that number outside of our function? Does it affect the x-coordinates or the y-coordinates? The y-coordinates, yeah, because it's on the outside. This is going to be 3 times each y-coordinate. C-O-O-R-D. Okay. 3 times every single y-coordinate. So if I'm here at the point 4, 2, and 1, 1, and label those initial points there, what does 1, 1 turn into? 1, 3. The x stays the same. The y changes. So we get, instead of 1, 1, we get 1, 3. And what's 4, 2 going to turn into? The x stays the same. And what does 4, 6? Very good. What happens with 0, 0? It stays 0, 0. Okay. So what I'm going to do then, 0, 0 stays, 1, 1 gets multiplied by 3, and it becomes 1, 3. So do you see how it's 3 times taller? And then 4, 2 turns into 4, 6. And there it is. And that is your stretched up curve G. Absolutely love doing this. I think it's super fun. All right, what's the 1/2 times my function going to do? What is the 1/2 going to do in front of my function? Yeah, it's 1/2 of the y coordinate. That says coordinate. All right, so 1, 1 was my original function. And so what's the new point become? 1 and then 1/2, or 0.5. And what does 4, 2 turn into? 4, 1. Very good. And so those are the points I'm going to graph. It gets smaller by 50%. So 4, 2 shrinks vertically. So it's a vertical shrink by a factor of 1/2. So this one is now half as tall as it started. Okay. And then we can connect those little dots in that same shape. So that's our H curve. All right, what about number 4? What's going to happen to our parent square root swoop? Yeah. And flip, bigger and flip. Very good. So it's -2 times the y-coordinate. And so it works all in one, which is kind of nice. So again, back to my parent function here. What does 1, 1 turn into? 1, -2. And what does 4, 2 turn into? 4, -4. Good. So we get the point 1, -2. 0, 0 stays. And 4, -4. So it flips and grows. And there's J. So that all of those numbers were out in front, and so every one of those numbers affects things vertically with our vertical axis, our y-axis. Now, on 5, 6, 7, and 8, all these numbers are inside with x, and so they're going to affect x or y coordinates. X coordinates. So we're going to start with our parent function, our square root swoop. So that again goes through 0, 0, 1, 1, and 4, 2. And so there's our square root swoop function. All right, now remember, everything with x is always messed up. So the square root of 2x. Divide. Yeah, I'm going to just flip the fraction because I think it's easier. So instead of multiplying by 2, we're going to divide by 2, or that's the same as multiplying by half. Okay? So it's half of the x-coordinate. So again, I'm starting at the point 1, 1 and the point 4, 2 on my regular curve there. So what do my new points turn into? 1/2. 1/2 times the x-coordinate. 1/2, 1. And what's the second point? 2, 2. Half of 4 is 2. The y-coordinate stays the same. So what's happening here is this point is shrinking closer to the y-axis. We're at 1/2, 1. It stays right in line horizontally, but it shrinks closer in. So 4, 2 shifts closer right there to 2, 2. And we get this. You see how it's squishing closer to the axis? So that is a horizontal compression. It's like a spring getting compressed closer to the y-axis. All right. Instead of 1/2 times x, what's it going to do? 2 times x. Yeah, flip your fraction. Becomes 2 over 1 times the x-coordinate. All right. So our original point 1, 1 is going to become 2, 1. And the original point 4, 2 is going to turn into 8, 2. So now it's 2 times the x-coordinate. It always just flips with x. It's just always weird. So we have the point 2, 1. So that is moving away. It's stretching horizontally, stretching away from that x-axis. And then we have the point 8, 2 right there. 4, 2 stretched outward, away. So this is a vertical stretch by a factor of 2. Oh, sorry, horizontal stretch by a factor of 2. All right, this J here, what's that going to do? Yeah, this is a negative inside with x. So that's going to reflect it horizontally. So it's going to reflect it over the y-axis. So it's going to flip over this way. What's the 4 going to do? Divide by 4. Or I can just change and say, we're going to multiply the x-coordinate by negative 1/4. We can take care of it all at once, which is kind of nice. So instead of multiplying by negative 4, we're dividing by negative 4, which is the same as multiplying by negative 1/4. So let's see. 1, 1 becomes negative 1/4, 1. That's very close to the axis. And then 4, 2 becomes negative 1. Yeah, 1/4 of 4 is just 1. So negative 1, the 2 stays the same. All right. So we're at 0, 0. We go left 1/4 and up 1. It's very close to the axis. And then negative 1 to 2. And so it flips and shrunk in a ton. And so there is J. And of course, all these have numbers, so you could check them on your calculator, which is kind of cool. And you can look at those points and see that they match, which is kind of cool. All right, let's look here. This sort of mixed bag, last one. So I have my parent function here. What shape is x squared? Parabola. Goes through 0, 0, 1, 1, and 2, 4. And then they're reflected across the y-axis. So here is our parent curve, And I'm just going to label a couple of points here, 1, 1, and 2, 4. So we have a couple of points, and there is our parent of function f. All right, the 3, it's on the outside. Is it going to affect the x or the y? The y, yeah, this is 3 times my function. So this is 3 times the y coordinate. And so 1, 1 is going to turn into 1, 3. And then 2, 4 is going to turn into 2, 12, which is off of my paper, but that's okay. 0, 0 stays 0, 0. We get 1, 3. So you see how it's stretching vertically? That point is just stretched away from the x-axis, just taller. And then 2, 4 would be like way up here. And so we get a very much like, it looks skinnier, but really is taller. It's that Buddha baby thing. This is G. That's our G graph. It just gets stretched taller, makes it look thinner. I wish I would grow taller, because then I would look thinner. Okay. All right. Number 11. Is that 2 going to affect the x or the y coordinate? It's going to affect the x coordinate. What's it going to do? Half the x coordinate. Yes, half the x coordinate. And so my 0.11 is going to become 1/2 1. And the 0.24 is going to become 1/4. Yep. All right, so 0, 0 stays, and then I'm at 1/2 1, and I'm at 1/4. So this is a very skinny again. So what's it doing from the red graph to the pink dots? This is a horizontal compression. Do you see how that it's pulling in towards the middle there? So that's a horizontal compression. So there's H. All right, last one. What's going to happen on number 12? Good. So we have -3 times the y coordinate, and not multiplying by 1/2, but rather flip it. So 2 times the x coordinate. So this is changing both the x and the y. So let's see. 1, 1. The x gets doubled. And then the y gets multiplied by 3. So 2, -3. Good. And then 2, 4. The x gets doubled. So 4. And the y becomes -12. Good. 0, 0 stays the same. So we have 2, -3. That would also be -2, -3. And then 4, -12 would be way down here. So we are, a couple things happening here. That's J. Let's see, this is a vertical reflection and stretched by a factor of 3. And then this is a horizontal stretch since our x values are getting bigger. All right, horizontal stretch by a factor of 2. All right, are you okay with that? Yeah. Okay, that's what you're doing today in the Delta Math. So you have to look and change the points. So today is not so much about moving whatever the central dot is, but moving 1, 1, where should it go if you're changing the ordered pairs? So let me release that.